The next time you're on one of those sleek, driverless trains, just think about this for a second. It's not run by a single giant brain. It's actually a super high-speed digital conversation. And, well, sometimes those conversations turn into some pretty dangerous arguments. So today, we're going to pull back the curtain on that invisible world that makes these trains run and what happens when they start to disagree. Right, so your first thought is probably to picture some kind of super smart computer sitting in a room somewhere making all the calls, a central brain controlling everything. But the reality is actually way more complex and honestly a lot more interesting than that. The truth is, an automated train is this whole network of different systems. You've got sensors on the wheels, controls for the brakes, computers figuring out the location, and they're all chattering back and forth thousands of times a second. And the safety of every single passenger? Well, it depends on every one of those parts telling the exact same story all the time. Okay, so to really get what happens when things go wrong, we first have to understand how they're supposed to go right. Let's start with the basics of the system that's running the whole show. The official name for this brain is automatic train operation, or just ATO. The best way to think of it is like the train's central nervous system. It's constantly pulling in data from everywhere, sensors on the track, the train's own controls, communication networks, all of it, just to orchestrate a perfectly safe and efficient trip. So what happens when that constant conversation breaks down? When one part of the system is screaming, go, and another part is screaming, stop. This is where we get to the absolute heart of this whole thing, the critical problem of data inconsistency. And this right here is the crucial definition. Data inconsistency isn't just a simple glitch, it's a full-blown conflict. It's what happens when the system gets two or more pieces of information that totally contradict each other. All of a sudden, it has no idea what the real truth is. And in a system hurtling along a track, uncertainty is the absolute last thing you want. This really gets to why this is such a wicked problem to solve. Look, a simple fault is one thing. A sensor breaks, the system knows it's broken, and it can work around it. But with an inconsistency, both sensors might look like they're working perfectly fine. They're just telling two completely different stories. Is the track ahead clear, or is it occupied? The system is getting two different truths. So the critical question becomes, which one do you believe? And this is where the research that inspired this explainer is just fantastic. It doesn't just say, hey, inconsistencies happen. Nope. It actually breaks them down, categorizes them, and creates this sort of field guide to all the different ways a train can argue with itself. So the paper breaks these digital arguments down into 7 key categories, and by understanding these specific types of conflicts, engineers can start building systems that are smart enough to actually resolve them. Let's walk through a few of the big ones. First up, interlocking feedback errors. Okay, the interlocking system is the absolute bedrock of railway safety. It's the physical system of switches and signals that is designed to prevent two trains from ever being on the same piece of track. An error here isn't just a glitch, it's a potential disaster. So imagine this. The main computer thinks a track switch is safely locked into position, and it gives a train the green light to proceed at full speed. But in the real world, the track is actually misaligned. That's a digital lie that could lead to a catastrophic physical reality. Next up, we've got sensor-level discrepancies. These are basically the train's eyes and ears on the track itself. We're talking about things like axle counters that count wheels going in and out of a section, and these things called balises, which are like digital signposts on the track. And yeah, sometimes what they see and hear just doesn't line up. Here's a perfect example of the paradox an ATO system might face. The axle counter is saying, I counted wheels going in, but not out, so this track is definitely occupied. But a sensor on the track itself tells the approaching train, nope, all clear. The system is totally stuck. What does it do? The only safe option is to stop. And just like that, a tiny data glitch can bring the entire line to a grinding halt. This third category is all about timing. See, in a system where decisions are being made in milliseconds, when a message arrives is every bit as important as what it says. A little bit of network lag can cause messages to show up out of order, which can trick the system into making decisions based on old, totally outdated information. Yeah, just picture it. The train gets a green light message, but it shows up a second too late. The information itself was right, but now it's completely useless. The system, because it didn't get the confirmation in time, may have already slammed on the emergency brakes, assuming the absolute worst. This is a massive and super frustrating source of delays. And the research covers even more ground. It also identifies stuff like simple communication errors, lost or garbled messages. Then there are redundancy conflicts, which is literally when your main system and your backup system start arguing with each other. You've got environmental issues, like heavy fog fooling an optical sensor. And of course, the classic, a human-induced error, where a manual override messes with the automated system's head. So we've gone through all these technical glitches, but why should you, as a passenger, actually care? Because these invisible arguments have very, very visible consequences. Let's take a look at the real-world domino effect. This table really puts it all into perspective. Just look at that efficiency impact column. Yeah, that's your commute. Notice that pretty much every single type of inconsistency has a high impact. Those interlocking and communication errors, they're the worst of the worst, hitting both safety and efficiency hard. Even something that's only a medium safety risk is almost guaranteed to delay your train. This breaks down exactly how that little glitch turns into a massive delay. It all starts with the data conflict. That creates uncertainty. And to guarantee safety, the system has to slam on the brakes and default to its most cautious setting. The result? A service disruption. So that sudden, unexplained stop in the middle of a tunnel, it could very well be that ghost in the machine, just having a little argument with itself. So I know this all might sound a bit unsettling, but the point of this research isn't to scare us, it's to empower the engineers who build these things. Because once you can actually name and categorize a problem, you're officially on the path to solving it for good. And that's exactly why this research is so valuable. This field guide of 7 glitches gives designers a shared vocabulary. Now they can build simulators to specifically test for these kinds of digital arguments. They can design smarter systems that, instead of just shutting down, can intelligently analyze conflicting data to figure out what's really going on. And like the authors say in their conclusion, this is all about building the next generation of automated systems. We're moving beyond systems that are just fail-safe and towards systems that are resilient. Ones that can handle the messy reality of conflicting data and keep right on performing safely and efficiently. And that really leaves us with a fascinating final thought that goes way beyond just trains. From self-driving cars to automated power grids, we're building a world that runs on these incredibly complex digital conversations. The real challenge ahead isn't just about making our machines talk to each other. It's about teaching them how to handle disagreement, how to argue constructively, and ultimately, how to work together to find the truth.